Okay, here we are again. We're looking at Chapter 7. We're looking at quantum mechanical model. This is going to be gearing us up towards kind of how our understanding of electrons and electron structure in an atom functions. So that's kind of the big goal here. Now to talk electrons, we need to talk light. So the light that we see is called visible light, and it is an example of what we call electromagnetic radiation. Also called radiant energy. You can carry energy through space. It radiates outwards. And there's lots of types of electromagnetic radiation like visible light, radio waves, infrared, X-rays. All those are examples of electromagnetic radiation. The light that we see is just, well, it's just a type of electromagnetic radiation that we have sensory organs that are attuned to. Now, all electromagnetic radiation travels through a vacuum at a speed of 3 times 10 to the 8th meters per second. We call it the speed of light. It's lowercase c. Again, it could just as easily be called the speed of radio, but we knew about light first because we can see it. Electromagnetic radiation kind of looks like this. There's two components to it. There's an electrical field component and a magnetic field, and they actually operate at right angles to each other, and as one generates, the other one gets generated too. It's really cool that way. Anyway, there are electromagnetic waves. So waves are periodic, which means they regularly repeat. The distance between two equivalent parts of a wave we call a wavelength, shown by that lambda there. And the number of complete wavelengths or cycles that passes a certain given point each second is called its frequency, or nu. There is a relationship between speed, wavelength, and frequency, which is given by this equation here. Speed of light equals frequency times wavelength. And what this means, since all electromagnetic waves travel at the same speed, the speed of light, that means that as one of those numbers is higher, the other is lower. They're inversely proportional to one another. So high wavelength means low frequency. High frequency means low wavelength, and vice versa. Frequency is expressed in terms of an inverse second. You may see that in some of your problems, also known as a hertz, the most painful of all units. And wavelength will be in meters, most likely because it is a length. But you also might see some really small meters like nanometers, picometers, things like that, not uncommon. This is kind of an example of the electromagnetic spectrum, and again we can see that visible light is just this tiny little chunk right there. You do not need to know these values. What you probably should know again is that visible light is a small piece of that. And in terms of frequency, violet light is the highest frequency light we can see. Red is the lowest frequency light we can see. Radio waves are the lowest frequency energy, then microwaves, then infrared, then visible light, then ultraviolet, X-rays, and finally gamma rays. Now, there are three phenomena dealing with light that are not explained by light being a wave, and this is what kind of led to the idea of the electron. First off is the emission of light from hot objects. We call that black body radiation. There's the emission of electron from metals on which light shines. We call it the photoelectric effect. And finally, the emission of light from electronically excited gas atoms, which we call the emission spectra. So, hot objects and the quantization of energy, or black body radiation. Now, when solid objects are heated, they emit radiation. Oftentimes, they glow. They give off visible light. Think about like an electric stove, or if you've ever seen like a piece of iron or steel that's been put in a forge. It glows. It's heated. It emits radiation. Yeah. Now, what we know is that the wavelength of light radiated depends upon the temperature. A red-hot object is cooler than a white-hot object. Now, in the late 19th century, physics did not have an explanation for this. But in 1900, Max Planck figured out how to handle this. What he did is he assumed that energy can either be released or absorbed by atoms in only discrete chunks of some minimum size. And he called that smallest quantity of energy that could be emitted or absorbed, in other words, one of those chunks, a quantum. Now, what Planck then did is he proposed that the energy of a single quantum is going to be equal to some constant times its frequency, or E equals h nu. Energy equals some constant times the frequency. H, because Planck proposed this, it's called Planck's constant, and there's the value there. Now, according to Planck's theory, matter is only allowed to emit and absorb energy in whole number multiples of h nu. Because what we were seeing is that when we were heating up objects, it would be kind of the same color until a certain temperature hit, and then it would switch over. There wouldn't be in between things. So he's saying it can only emit that light, only emit that energy in certain multiples. That's why there's no in between. So you can emit and absorb like h nu, 2h nu, 3h nu, so on and so on and so forth. Now, if the energy emitted or absorbed was 3 of the h nus, we would say that the atom emitted 3 quanta of energy. Now, because the energies can be released only in those specific amounts, which we call a quanta, we say that the allowed energies are quantized. And that means that their values are restricted to only certain amounts. Now, does this seem odd? Think of this kind of like stairs. You can only step on stairs, not in between them. Likewise, energy can only come in certain amounts. There's no in between those amounts. Now, the question then comes, well, why don't, if this is the rule, if energy can only be absorbed or released in these set amounts, why don't we see this more frequently? Well, it turns out that because Planck's constant is so small, that on a large scale like we're looking, energy amounts seem continuous. It seems like there's all possibilities between 2 points, but only when you look at energy on a very, very, very small scale does it appear to be quantized, as that stairs appear to happen. It's kind of like if you have stairs built into a hillside and you're looking from very far away, it might look like a smooth path up, but when you get close up, you can see the individual stairs. Kind of like that. Now, so we have this idea of quantized energy. In 1905, Albert Einstein, yes, that Einstein, used Planck's quantum theory to explain what's called the photoelectric effect. And what photoelectric effect says, when photons of sufficiently high energy strike a metal surface, electrons are given off. And we knew that when you shone light of sufficient energy on metal, it would emit energy, it would emit electrons. We knew that. Now, for what we found is for each metal, there's some minimum frequency needed. If we go below that frequency, no electrons will be emitted. So explaining this, so to do this, Einstein assumed that radiant energy, aka light, striking the metal is acting like a tiny stream of particles or energy packets and not like a wave. And he called each of those energy packets a photon. Now, following Planck's quantum theory, he decided that each photon must have an energy consistent with Planck's equation, so the energy of a photon would be E equals h nu. Now, how this works, under the right conditions, a photon strikes a metal surface and is absorbed. Light shines on the metal absorbs the light. The energy from that photon is transferred to the electron in the metal. Now, there's a certain amount of energy needed. We call this the work function. And that's the energy required for an electron to free itself from the metal, free itself from the bonds holding it back. If the photon has less energy than that work function, less energy than that minimum amount, the electron can't escape and no electrons fly off. But if the photon has enough energy, electrons are emitted from the metal with that extra energy appearing as the kinetic energy of emitted electrons. Think of this like buying something. If you're trying to buy something that costs $10, and you offer someone $8, they're not going to give it to you. But if you try to buy something for $10 and you give them a $20, you get the thing and $10 back. That's kind of what happens here, that once you meet that work function, that minimum amount, you've kind of purchased, I'm doing air quotes around that, purchased the electron. It comes free of the metal, and any extra energy is turned into kinetic energy, allowing it to fly away. So now we're on 7.3. So atomic spectroscopy or emission spectrums. So Planck and Einstein's work opened up doors for understanding about how electrons are arranged. Now, in 1913, Danish physicist Niels Bohr came up with a theoretical explanation of line spectra. Well, what are these? So we know that a particular source of light may emit a single wavelength. And we call radiation composed or light composed of a single wavelength that's called monochromatic. Most light sources produce lots and lots of different wavelengths we call, so that'd be polychromatic. If you take, like from a light bulb, so if you take the light from a light bulb and you separate it into its individual wavelengths, we get a spectrum, which is the fancy name for a rainbow. Ooh, spectrum. Now, not all radiation sources produce a continuous spectrum. So if we take different gases and we place them in a tube and we apply a high voltage, we give them lots of energy, the gases will emit light. If we take that light and pass it through a prism, well, first off, the light given off is different colors. Now we pass that light through a prism, what we see instead of a full rainbow, we see only specific lines of color with big gaps in between. So this is kind of a picture of that. So we take hydrogen, we take that light, we pass it through a slit that just polarizes it, makes it easier for the prism to work with. Passes through the prism, we put it onto photographic film, we look at, and hey, now we have these individual lines, not a rainbow. We knew about this. Now, the colored lines are separated by black regions like we saw. And what we say is that the black regions correspond to wavelengths that are absent from the light. Now, a spectrum containing radiation only of specific wavelengths, like with that hydrogen that we saw, is called a line spectrum. So here's some examples. So up top we see helium's line spectra, there's barium's line spectra. This is contrasted with a white light spectrum, aka a rainbow. Now in 1885, Swiss schoolteacher named Johann Balmer showed that the wavelengths of the four visible lines of hydrogen fit a simple equation. Balmer's equation was later extended to a more general use and called the Rydberg equation. I'm going to show this to you. You don't need to worry about it. This is the Rydberg equation, and what it lets you do is it lets you calculate the wavelengths of all of the lines of hydrogen. You plug in any two positive integers, as long as n2 is bigger than n1, and then you solve for a wavelength there, and that is a wavelength that is present from the hydrogen. What's neat about this and what I love about this is we knew this equation worked, but we didn't. It took over 30 years to explain why this worked. All we knew is it worked. But again, you do not need to know this equation, just showing it to you. Now, Bohr ran with this. Bohr refined on Rutherford's model of the atom using Planck's idea of quantized energy. And so what Bohr did, kind of ran with this idea, is he said, only orbits of specific radii corresponding to definite energies are permitted for the electron in a hydrogen atom. Second, an electron in a permitted orbit has a specific energy and is in an allowed state. An electron in an allowed energy state will not radiate energy and therefore will not spiral into the nucleus. Third, energy is emitted or absorbed by the electron only as the electron changes from one allowed energy state to another. This energy is emitted or absorbed as a photon equals h nu. So we can see this is where that progression went. So again, Planck figured out the E equals h nu. Einstein just the h nu. Einstein figured out this photon idea having energy of h nu. And now Bohr is saying we're seeing those lines because each of those lines has a certain energy, certain frequency, and those are tied to that equals h nu, and that's happening where that energy, those photons are being emitted as an electron is jumping up to or falling down from these different allowed energy states. Now, the energy states of a hydrogen atom, you do not need this calculation. You can do this. So that's the energy that's allowed. H is Planck's constant, C is speed of light, R is Rydberg constant. You do not need to know this equation. A bunch of stuff there. Now again, what about that n there? This again is going a little bit further than AP chemistry needs, but I like this. The integer n, which can be between any integer between 1 and infinity, is called the principal quantum number. Each orbit in Bohr's model, each energy state corresponds to a different value of n, and the radius gets larger as n goes up. So the first orbit would be n equals 1. That's the orbit closest to the nucleus. Next would be n2, n equals 2, or so on and so on and so forth. Now the electron in a hydrogen atom, now again remember this is all about hydrogen. The electron in a hydrogen atom can be in any allowed orbit, and the previous equation would tell us the energy it would have depending on its orbit. Now, the energies of the electron in a hydrogen atom will always be negative. The lower or the more negative the energy is, the more stable it will be. The lowest energy is when n equals 1. So we call that the ground state of the atom. That's where the electron is going to be as its default. When the electron is in a higher, less negative orbit, the atom is said to be in an excited state. Now, What happens to the orbit radius and energy as n becomes infinitely large? Well, as the radius increases, we eventually reach a point where the electron is completely separated from the nucleus. And so basically, when n equals infinity, E equals 0. So that's why, again, these energies will always be negative. If the energy is ever 0, the electron is now removed from the atom itself. And you can see that from here, but again, don't worry about that, really. So the state in which the electron is removed from the nucleus is the reference or zero energy state of the hydrogen atom. This zero energy state is higher in energy than the states of negative. Again, 0 is bigger than negatives. That's how it works. And now in his third postulate, Bohr assumed an electron could jump from one allowed energy state to another by absorbing or emitting photons. But the trick is those photons' energy must exactly meet the energy difference between the two states. Or we can view that radiant energy is emitted when the electron jumps to a lower energy level, but then it's falling from one level to another, and it's always going to emit, again, a specific amount. So here's kind of an idea. So looking at the hydrogen atom, when an electron jumps from the third energy level down to the second, it emits a set amount of energy. That energy will always make that 750 nanometer wavelength red color. Likewise, when the electron jumps from the fourth energy level down to the second, we see that as blue-green. From the fifth energy level to the second, we see it as violet. Now you might be wondering, why am I stopping at the second? Why don't I talk about the first? Well, these are the only options visible to the human eye. These other ones work. We could drop from the second to the first, but that energy amount would be outside human perception. So we don't worry about it when we look at it. Now, photoelectron spectroscopy. This is a procedure where we also called PES. This is a procedure where high energy photons, usually ultraviolet or X-ray, are fired in an atom and absorbed. And basically we want the energy of these waves to be greater than the energy needed to ionize that atom. That way there's extra energy for those ejected electrons to be carried off in the form of kinetic energy as they fly away. Now, why do we worry about photoelectron spectroscopy? Because it's on the AP test. That's really it. Basically, one of the guys who wrote the curriculum for AP Chemistry, this was his baby and pet project, and so that's why it's on the AP test. Anyway, so what will we get when we do PES? We get data, and we see peaks, and the peaks are plots that show how many electrons are emitted at a certain amount of energy. From that, we can actually eventually identify things like the atom itself. Now, a few notes about this. I'm going to show you a couple pictures. The higher the peak, the more electrons are removed. So if there's two peaks and one peak is twice as high as the other, the one that's twice as high would have twice as many electrons in that particular energy state. So for example, here's magnesium. So if we do PES on magnesium, so again, we see kind of 3 peaks, roughly equal height, and one peak 3 times as high as the others. That means that this peak would contain 3 times the number of electrons. Now, the trick of this is that there's energy along this x-axis there. The lower the energy, the less energy it took to remove that. So it was easy to remove these first 2 electrons. Then it's harder to remove these 6. Harder still to remove these 2. And finally, much, much, much harder to remove these 2. That's PES. Okay, so now that we have Bohr's model for the hydrogen atom, this dual nature of radiant energy became a familiar concept. So again, dual nature meaning acting as a wave and acting as light, acting as a wave in the traditional sense, and also acting like a particle, like a photon. And that's what I say there. Now, Louis de Broglie extended this idea dramatically and weirdly. So, de Broglie said if radiant energy could behave like a stream of particles, could matter behave like a wave? So think about like an electron orbiting a nucleus wasn't thought of as a particle orbiting, but as a wave with a particular wavelength. And those of you who have dealt with this in math know that we can model circular behavior in terms of wave mechanics. So de Broglie suggested that its motion, the electron's motion on a nucleus, could be associated with a particular wavelength. And he went on to propose that that particular wavelength of the electron or any other particle depended upon its mass and velocity, which brings us to the de Broglie equation. This is the de Broglie equation. So the quantity mv, so this mv there is also known as momentum when you take physics. H is Planck's constant. So really just take Planck's constant, divide it by its mass times velocity. And so any object with mass that is moving, has velocity, has a wavelength. Now what this means, again, it applies to all matter, not just electrons. Any object with mass and velocity has or is a matter wave. But the larger the mass is, the smaller the wavelength becomes. Now most ordinary objects that we deal with have such a small wavelength, it's completely out of the range of any possible observation. But electrons are so small, though, that they will still have some applicable wavelength, and a reasonable one. So, for example, what is the wavelength of an electron moving with a speed of 5.97 times 10 to the 6th? That should be meters per second. Meters per second. The mass of an electron is 9.11 times 10 to the negative 28 grams. Key of this is that the de Broglie equation only works if mass is in kilograms and velocity is in meters per second. So, again, velocity had to be in meters per second. To turn that into kilograms, we just take the grams and divide it by 1,000. So 9.11 to the negative 28th divided by 1,000 is 9.11 times 10 to the negative 31st. And again, the wavelength is Planck's constant, 6.63 times 10 to the negative 34th over the mass, 9.11 times 10 to the negative 31st times its velocity, 5.97 times 10 to the 6th. And I plug that all in my calculator, which I am, oh my God, I'm putting the wrong buttons. 6.63 to the negative 34th divided by 9.11 to the negative 31st times 5.97 to the 6th. And I get a wavelength of 1.22 times 10 to the negative 10th. Now, where this becomes interesting is if we think about this in terms of length and whatnot, the angstrom is a 10 to the negative 10th. 1 angstrom is the distance between a nucleus and the electron in a hydrogen atom in its ground state. And that's what we're seeing here for the wavelength. So that's kind of neat. I like that. Now, what's the use of this? This is used practically in electron microscopes. You really don't need to worry about overly much. Just kind of a neat, hey, how about that? Isn't it cool sort of thing. Likewise, kind of weird stuff with here, the uncertainty principle. So Werner Heisenberg proposed that the dual nature of matter places limitations on how precisely we can know the location and momentum. This is called the uncertainty principle. Basically what it means is the more we know about where an object is, the less we know about its momentum. That means its mass and velocity. We can either know a very small amount about both, or we can know a lot about one and almost nothing about the other. That's just how that goes. Okay, so starting now, things are going to start getting a little bit muddled. Just want to give you a heads up on that. So this then leads us to the quantum mechanical model of the atom, which is kind of our modern view and what kind of underpins pretty much everything else for the rest of the material for the year. So Austrian physicist Erwin Schrödinger proposed an equation called Schrödinger's wave equation. And Schrödinger's wave equation incorporated both the wave-like behavior of light and of electrons and the particle-like behavior of electrons. So it's all about electrons, and it's recognizing both that particle and wave nature. Now, this opened up the field that we kind of refer to now as quantum mechanics or wave mechanics. This equation requires advanced calculus to deal with. If you become a chemistry major or a physics major, you will deal with the Schrödinger equation somewhere around your senior year as an undergraduate. So again, a bit above your current pay grade. Now, this led to this idea of orbitals, kind of where the electrons are and in terms of their energy. So, along with this, you may notice there's these letters, N's, L's, M sub L's. Those are called quantum numbers. We already have seen like the principal quantum number, N equals 1, 2, 3, so on and so forth. That's the energy level. You can use some combination of N, L, and M sub L to define where an electron is. And we call where those electrons are our orbitals. That's what you need to know for AP chemistry. Now, this idea of valid or invalid quantum numbers is a thing. But that is beyond the scope of AP chemistry. It was removed from the curriculum a couple years ago. You don't have to worry about it. But just kind of want to point that out. And when we talk orbitals, again, that's really where electrons are. Okay. So looking at that again, each box represents an orbital. That's what we see there. Talk about that. Orbits of the same subshell, such as 2p, are grouped together, and we see that. So like here's the 2p. So in the second energy level, n equals 2. In the p-type orbital, so we call it the sublevel 2p, there are 3 possible orbitals, each with the same energy. That's why they're grouped together. Now, when the electrons are in the lowest energy orbital, the hydrogen atom is said to be in its ground state. When the electron is in any other orbital, then we call it in the excited state. Let me erase that so it's a little bit less distracting. Now, the electron can jump to that excited state by absorbing a photon of just the right energy, just like we saw previously. So now we're into 7.6, the shapes of atomic orbitals. This you need to know. So now we're going to look at how we picture orbitals. So the s orbital, pretty straightforward. So the 1s orbital is the lowest energy orbital of the hydrogen atom. 1s is its sublevel, and there's only 1 electron, so we can also have the 1s orbital. Now the electron density for the 1s orbital shows that the 1s orbital is spherical. Look, it's a sphere. All other s orbitals are seen to be spherical as well. Now the reason for this, and this gets a little bit more detail than you need, but I think it's kind of interesting. So again, all s orbitals are spherical, and this is on page 323 of your book. This is the output. This graph that you see is one of the outputs of the Schrodinger equation, and what the Schrodinger equation shows you is probability. And what this shows us is that there's a point at 52.9 picometers. Darn it, 52.9 picometers of maximum probability. And the idea is you kind of take that probability piece and you spin it in space, and it carves out a location. And that's basically because it's just that single peak that you spin around its axis, creates a sphere, and that's why we say it's spherical. So yeah, that's what we see. So again, yeah. The 2s would have 2 peaks for probability and 0 probability at 1 angstrom. So this is what we see there. So there's kind of these 2 little peaks on the 2s. We see this area of 0 probability, and then 2 peaks. 3s, kind of same thing. We see 2 areas of 0 probability, and then we see peaks. Where probability is 0, you get what's called a node. And again, that's where we saw probability is 0. And that's the higher up you get, the larger range of where an electron could be, more spread out area. 3s is even more spread out. The secret to this and the takeaway is that the higher the energy levels, the 1s, 2s, 3s, that number in front is the energy level. That's the principal quantum number. The larger that is, the more spread out the area is, the larger the sphere is. Now, what's interesting about this is that technically it's not a real sphere. There's little gaps in there, kind of like a donut. And so there's regions of space where the electrons have 0 probability, and that's those nodes. You don't need to worry about that. That is well beyond our current scope, but it's interesting, and so I thought I would mention it. And again, that's what we see there. Again, what does this all mean? That means as n goes up, there's also an increase in the most likely distance from the nucleus to find an electron, which means size it goes up as n goes up. That's the takeaway. That's what you need. P orbitals are shaped like this. There's 3 of them, one along each of the principal axes. Again, this is kind of how it looks. These are kind of how we visualize it. So we can see that there's these 2 areas of electron density on either side of the nucleus. We call those lobes, whereas where the nucleus in the center is would be, again, another node where we're not going to find electrons. Beginning with the second energy level, each shell has 3 space p orbitals. So there are 3 2p orbitals, there are 3 3p orbitals, 3 4p orbitals, so on and so on and so forth. For each value of n, they have the same shape, but different. Again, for the same value of n, they have the same shape, but different spatial orientation, meaning they're flipped on x, y, and z axis, and that's what we see there. And again, they increase in size with increasing n values. D and F, once n is 3 or greater, we then get 5 d orbitals. This is the shapes of the d orbitals. You do not need to know those. They're just there. And when n is 4 or greater, we get 7 equivalent f orbitals. And this is what f orbitals look like. Again, these are all the outputs from the Schrödinger equation. Now we're going to skip a little bit, so we're moving into 8.3. So yes, we've moved chapters, but I want to figure while we're talking this, let's talk electrons. We're going to move through this very fast. It is no harder than it was in your normal chemistry class. So we're now going to consider the arrangement of electrons and atoms. We do this by finding what's called its electron configuration. The most stable electron configuration, aka the ground state, is where the electrons are in the lowest possible energy states. If there was no restrictions on where electrons would go, they would all go into the 1s because that's the lowest in energy. But the Pauli exclusion principle tells us there can only be 2 electrons in any given orbital. That's the rule. Now, orbitals get filled in order of increasing energy, so with no more than 2 electrons per orbital. So we're going to consider lithium. Lithium has 3 electrons. The 1s orbital can hold 2 electrons, so the third one goes in the next lowest energy orbital, the 2s. So we represent electron configurations by writing the symbols for the occupied subshell and adding a superscript to indicate the number of electrons. So lithium would be 1s2, 2s1. Again, 2 electrons in the 1s sublevel, 1 electron in the 2s sublevel. One way we can do this is if we kind of write those boxes. So think back a few slides. We can represent electrons as arrows. Each of these boxes represents an orbital. So again, we put 1 in the 1s, or 2 in the 1s, and then 1 in the 2s, because there's 3 electrons to fill up. Electrons having opposite spins are said to be paired when they're in the same orbital. An unpaired is when they are not paired up. It's pretty straightforward. So with the lithium atom, the 2 electrons in the 1s would be paired, but the electron in the 2s would be unpaired. Excuse me while I drink some refreshing water. Hydrating. So this leads us to Hund's rule. When placing electrons in orbitals, we follow energy trends. We have to fill the lowest energy levels first. But we run into problems once we get past boron. So boron has 5 electrons, so we would put 1 into 1s, a second 1 into 1s, opposite spins, that's the rule. 2 electrons, 3 electrons, there we go. So now we run into a problem because we have 3 of the 2p orbitals, and so we need to figure out which one we put them in. So where does that 6th electron go? We know it has to go into the 2p, but which one? It's answered by Hund's rule, and Hund's rule tells us that for energy orbitals of the same energy and type, we call those degenerate orbitals. The lowest energy is obtained when the number of electrons with the same spin is maximized. Basically, it means we're going to put 1 electron in each of the 2p orbitals, all with the same spin, before we start creating paired electrons. So a few examples. I actually kind of messed up on the boron one. My apologies because I forgot I said past boron. So carbon has 6 electrons. So we would go 1, 2, 3, 4, 5. Now technically there is no specific order because all 3 of these have the same energy. I would just go right to left. Don't make your life harder. So 5 and 6. That's what Hund's rule tells us to do. Fluorine has 9 electrons. So 1, 2, 3, 4, 5, 6, 7. Now we can start doubling them up. 8, 9. So that's how we would see. So this would have 1, 2, 3, 4, 5, 6, 7, 8 paired electrons and 1 unpaired electron. Hund's rule is based partially on the fact that electrons repel each other. Therefore, by going to different orbitals, we're spacing the electrons out as far as they can, minimizing electron-electron repulsions. So, for an example, we're going to write the electron configuration for phosphorus, element 15, and find out how many unpaired electrons does it have. I'll do it on this slide, and then I'll erase it. So phosphorus, again, has 15. So think of this in terms of my kind of energy diagram. So here's our 1s, 2s, 2p, all those are 2p, 3s, those are all 3p. So again, we're doing phosphorus with 15 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So writing its electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p3, and it would have 3 unpaired electrons. Now again, there's going to be an easier way to do this than what I was just showing with the boxes, but the boxes are a nice way to visualize what's going on until you have mastered, and it's more useful in terms of figuring out what's going on with the electrons. Now, condensed electron configuration. So neon fills out the 2p sublevel, and we'll have a stable configuration with 8 electrons. It would be 1s2, 2s2, 2p6. The 2p sublevel is filled, has 8 electrons. It's called an octet in its outermost energy level. The next element, sodium, marks the beginning of a next row on the periodic table. Sodium would have a single 3s electron be on the stable configuration of neon. And so what we can do is we can abbreviate the electron configuration for sodium based upon its relationship with the stable configuration for neon. What we do is sodium starts with neon, because neon, again, is the 1s2, 2s2, 2p6. Sodium is 1s2, 2s2, 2p6, 3s1. They both share that 1s2, 2s2, 2p6 piece. So we're substituting that with the neon, and then we just have that 3s1 left over. So we can always use a noble gas's electron configuration as a base for elements that come after it. So again, what did I do? The symbol neon represents the electron configuration of the 10 electrons of neon. By writing neon 3s1, it helps focus attention on the outermost electrons of the atom, which are the ones mostly responsible for chemical behavior. So again, to generalize, when we're doing a condensed electron configuration, the electron configuration of the nearest noble gas element of lower atomic number is represented by its chemical symbol in brackets. So lithium would simply be helium 2s1, because helium is the noble gas that comes before lithium. Now, we refer to the electrons represented by the symbol for the noble gas as the noble gas core of the atom. So with lithium, it would have a noble gas core of helium. For sodium that we saw, it would have a noble gas core of neon. Usually, these inner shell electrons are referred to simply as core electrons. The electrons after are called the outer shell electrons. Also, in the outer shell electrons, which includes the electrons involved in bonding, we call the valence electrons. That's going to be very important coming up. Now, for the lighter elements, for atomic number 30 and less, all of the outer shell electrons are valence electrons. It's just how it works. Things get odd in the heavier elements, mostly with the transition metals. So we know argon on the periodic table ends the row started with sodium. This is argon's electron configuration. It is a noble gas. The element following argon is potassium. Potassium is obviously a member of the alkali metals. Its outermost electron occupies an s orbital, but this means that the electron with that has the highest energy the electron did not go into the 3d, which does exist, but instead the 3d is skipped, and that extra electron goes into the 4s. So the condensed electron configuration for potassium is argon 4s1. Following complete filling of the 4s orbital, so starting with scandium and extending through zinc, then electrons are added into the 3d. So the 3d was skipped in favor of the 4s. And because we now have this extra D sublevel we're dealing with, that's why starting with period 4, the periodic table extends 10 elements wider. And we call all the elements in that extension the transition elements or transition metals. Now, how we fill in transition metals. So following the electron configuration for these follows Hund's rule. Electrons are added to the 3D orbitals singly until all 5 orbitals have 1 electron each. Then we double them up, make it happen. So for example, like with manganese here, I would start, so manganese is element number 25. I'm looking at a periodic table, so I see argon. So we would have, again, argon is number 18, manganese is 25. So we would need 7 electrons, it looks like. So 1, 2, 3, 4, 5, 6, 7. So that's what we'd see there. Zinc, same idea. Oops, my apologies. I should not be doubling up so quickly. And 4s2, 3d10, that's what we see. That's how it would fill it. Now, once we have the 3d orbitals filled with 2 electrons each, then the 4p orbitals get filled until we get a full octet of outer electrons. So like with krypton, we would end with 4s2, 4p6 in the highest energy level. And again, there's that full octet. 2 plus 6 is 8. Lanthanides and actinides, so the 6th row of the periodic table begins like the previous one. So we're now in period 6, starting with cesium. So 1 electron in the 6s orbital for cesium, 2 in the 6s for barium. But then the periodic table then has a break, and elements 57 through 70 are placed below the periodic table. This is where we get the new set 4F. So again, to get to that 6S, we've actually skipped this like 4F from the previous ones. And since there's 7 4F orbitals, it'll take 14 electrons to fill it. Again, 2 per orbital. These 14 electrons come from the elements known as the lanthanides or the rare earth metals. Now, because the 4F and the 5D orbitals are physically very close to one another, the electron configurations of some of the lanthanides involves 5D electrons as well. Basically, they cause things to start overlapping. There's weird exceptions. You do not need to know the exceptions. You do not. Just recognize there's oddness. There are exceptions. Final row of the periodic table is the actinide. Most are radioactive. Most are not found in nature. We're filling in the 5F. Okay, almost done with this. So we're going to look at section 8.4, looking at how we can find the electron configuration from the periodic table. This is much more useful than those box diagrams previously. So again, just by looking at the periodic table, we can determine the electron configuration. And what we do is we break the periodic table into blocks. So we can see here we have the S block. So that's the alkaline metals and the alkaline earth metals. This does include helium, by the way. Here we have the P block. So that's starting with boron through the noble gases. Transition metals would be the D block. Lanthanides and actinides would be the F block. So this is how we use this. We find the element we want. We find what block it's in. We then fill up orbitals until the block you're looking for. So you look at what should come before your target element. Count how many elements into the row you are. That's how many electrons are in that subshell. And then remember, for the S and P blocks, the period number is the coefficient, the energy level. For the D blocks, period number -1 is the energy level. F block is period number -2. So let's have some practice. Bismuth, atomic number 83. So I'm going to kind of recommend that you pause the video for a moment. I'm not going to pause, but pause the video for a moment. We find element 83. And I'm going to actually do this with an abbreviated configuration because that's just simpler. And then I'll do it with cobalt. So I find the noble gas before it, bismuth, is Bi. So xenon is the noble gas before that. So again, I find element 83. And now I'm filling up through there. So from xenon, I go, let's see, cesium, it's in the 6th period, so 6, I'm filling in the 6s, and I go over 2, so 6f's 2, because 1, 2 spaces. I'm now into the lanthanide series. So I go down to 4f, I have to fill up all those, 4f14. I now do the transition metals. Transition metals are period -1, so 5d10. And then I can see bismuth is the third element into the P block, so 6p3. We're going to do cobalt. Again, try to do cobalt on your own. Look at a periodic table. I'm going to walk through this. I don't have a picture of it on this. I'm well aware I'm not good at making videos. We get argon as our base, and then 4s, and again, we're filling up through cobalt, so we still have the 4s. Now, cobalt is in the D block. Because we're in period 4, it's going to be 3d. And cobalt is 1, 2, 3, 4, 5, 6, 7 in, so 3d7. And let's do tellurium. Let's do one more. So tellurium is element number 52. So kind of bottom right periodic table. So we're looking at krypton as our noble gas before it. We're in the 5th period, so 5s, and we're filling up both of them, so 5s2. There is no F block, so we go straight to the D. 4d, again, the D is one energy level less than the period. We're going through all of that, so 4d10, and finally we're going to end with 5p, and tellurium is the 1, 2, 3, 4th there, so 5p4. Pretty straightforward. Valence electrons, again, these are the outer shell electrons used in bonding. For representative elements, do not consider completely full D or F subshells to be part of the valence. For transition metals, do not consider a full F subshell to be part of the valence. So again, for the transition metals, don't worry about the F sublevels. For things in the S or P block, don't worry about the D or Fs. Now, as a note, some elements do have weird electron configurations. Most are going to be the F, but we're also going to see quite a few in the D block having weird electron configurations. You don't have to worry about them. They're treated as normal. So especially when we start talking ions, let me just show you an example of this. So let's talk iron. So iron is element number 26. So looking at its electron configuration, argon would be the noble gas before it. It's the 4th period, so 4s2, 3d, 1, 2, 3, 4, 5, 6. Now, as kind of a quick note, now that might not actually be iron's electron configuration. Again, we're in the D block. It might be a little bit funky. Weird things happen. But when something becomes an ion, so let's say when iron forms a 2+ ion, it's actually going to lose the electrons from the highest energy level first, so it'll actually lose these 4s. So we would assume it's argon 3d6. A little bit weird, but that's how it is. Anyway, that's it. That's the chapter.